Hello and welcome back to another episode of Math with Stone. Today we're going to be doing some simplification of some radical expressions that don't always have a square root. So you need to be looking at the index number, and if there is an index number, it will tell you how many of a kind you're looking for. So for number 3, that little 3 tells you you're looking for 3 of a kind. If there is nothing there, you're looking for a square root, and there is an invisible 2 that would denote how many of a kind you are looking for. Okay? So with the numbers, there's a few different methodologies for how to do this, but I recommend just breaking it up and dividing specifically by 2 for as many times as you can, because it's easy to divide by 2. All right? So I divided 24 up, and we ended up with 1, 2, 3 2's here. And I don't want 3 of them. I only need 2 of them because the number in front of a square root is looking for 2 of a kind. So I'm going to circle these 2's, and that value will go on the outside, which happens to be a 2. Then whatever doesn't get circled, this 2 and that 3, if there is multiple things, will multiply back together and be left on the inside. And this makes sense because if you really think about the square root of 24, you could think about it as the square root of 4 times the square root of 6. And the square root of 4, of course, is 2. So that is why we have 2 square root of 6 left over. All right? Now, what do you do if you got numbers and you have these variables with exponents? Well, actually, the number is dealt with the exact same way. We break down the 30 into 2 and 15 and 3 and then 5. But you may notice that the 30, we got a 2, a 3, and a 5. We don't pay attention to the 15 or the 30. They don't have any like terms. So if there are no like terms, it just stays as a 30. All right? Now here, we have to deal with the x's and the y's. And the easiest way to do that is to divide. And if you divide 4 by 2, you end up with 2 perfectly. None left over. But if you divide 5 by 2, you do end up with 2, but then there would be a remainder of 1. And whatever remainder you have is left on the inside as that exponent. And that kind of makes sense because if I listed out 1, 2, 3, 4, 5 y's, I would have 1 y on the outside from a pair, another y on the outside from a pair, and then a single y left over. That's the one that is left underneath the radical symbol, excuse me. All right, so here, for number 3, this is our first time that we have a number that is not a square root. You still break down the number 48 exactly as is. I am going to break it down as if it were a positive 48 because I feel like that makes it a little easier for right now. 2 and 12, 2 and 6, a lot of 2's. All right, because it's a cube root with a 3, a little 3 there, we are looking for 3 of a kind. I have 3 2's, 2, 2, 2. So that number is going to go on the outside. And then here we have a 2, and a 3 that did not get broken down. Those are going to have to multiply back and be on the inside. So this is going to turn into 2 cube root of 2 times 2 is 4 times 3 makes 12, which makes sense because that is what those all broke down into. So 2 times 2 is 4 times 3 is 12. We have a 12 here. Now the thing about odd roots, like cube roots or fifth roots or things like that, is that you can take the cube root of an odd number. And if you do have the cube root of an odd number, it will spit out an odd value. So I'm going to put a negative 2 in front on the outside. And I'm going to demonstrate why that is the case. So let's say we have the cube root of just something like negative 8. Okay? That is negative 2. Why is it negative 2? Because negative 2 times negative 2 makes 4 times another negative 2 times another negative 2 ends up equaling negative 8. And you're looking for what multiplies by itself 3 times to equal that middle number or the number underneath the radical. And in this case, cube roots and fifth roots and all those things can have the cube root of a negative number. If it is an even root, you can't take out the negative number because anything multiply negative times a negative, even amount of times, it equals positive. Multiply a negative times a negative times a negative, odd amount of times, it can equal the negative. All right, let's finish this part up. We got to break down the 256, which sounds like a lot. So I'm going to keep with my idea that dividing by 2 is just easier. However, you might realize that, it's annoying, but that doesn't mean that it is not easier. So we have a lot of 2s so far. Let's see how many more 2s I can end up with. We got 2 and 8, 2 and 4, 2 and 2. A whole bunch of 2s. We need 4 of them because it's a 4th root. So 1, 2, 3, 4. And 1, 2, 3, 4. So they all decided to be relinquished of that. So here we have 2 on the outside and another 2 on the outside. Just like when we had here where we had multiple things left over, they multiplied. Here we have 2 things we circle, they will also multiply. So 2 times 2 on the outside will make 4. Which apparently means 4 times 4 times 4 times 4 is equal to 256. So 4 to the 4th power apparently equals 256. Who'd have known? All right, so I'm going to do this in 2 parts. We got 4th root of y to the 6th, z to the 7th. All right, no value for a number was left over, so I didn't have a number here. This 4, not the one we took out, but the 4th root, we'll be taking and we're going to divide 4 by 6. Well, how many times will 4 go into 6? That would be 1 time, so we're going to have a y to the 1st. How many times will 4 go into 7? Also 1 time. Well, what do we have left over? We got the 4th root of, what do we got left over? We got 4 went into 6, 1 time with a remainder of 2. 4 goes into 7, 1 time with a remainder of 3. All right. Let's break down the 96. It is a 4th root. 4th roots are not allowed to be negative, so you might want to represent this as an imaginary number, but imaginary numbers are specific to square roots, so the 4th root won't work there. But that's okay. We can still break down the 96. We'd have 2 times 48. We'd have 2 times 24. Then we'd have 2 times 12. And then we'd have 2 times 6. And I'm not going to break down the 6 because I don't think I'm going to get any more 2s. So we can take out a 2. And we can't take out a negative 2 because a negative 2 would end up making a positive 96. So that's not going to be okay. So this is going to be positive 2 with a 4th root of whatever was left over, which was 6. But because I couldn't remove the negative, it's going to be 4th root of negative 6. All right. Oof, 972. That's going to be a lot of breaking down. So I'm gonna keep with my idea that 2s are easier. It might take more space. 972 divided by 2 ends up equaling 486. Divide by 2 ends up equaling 2 and then 243. I cannot divide by 2 anymore. Oh no! If I can't divide by 2, I try dividing by 3. And it does work when you divide by 3. You get 3 and then 9. Excuse me. 81. Now, I could divide by 3 again, but I know that 81 divides by 9. You're allowed to divide by whatever you want. I just recommend dividing by 2 and then 3 to kind of keep it organized. See how like all the 2s line up and then things like that? It just makes it a little more organized when you divide by the same value. We're looking for 5 of a kind. Well, look here. We don't have enough 2s, but we do have 1, 2, 3, 4, 5 3s. 1, 2, 3, 4, 5. It's either 1, 3, and then a 2, 3, 4, 5. So with that in mind, we're going to have a 3 on the outside. It is an odd root. We can take the odd root of a negative number. It's going to be negative 3 on the outside. 5th root of, well, what do we have left over? We got 2 2s. They end up multiplying back together to make 4. I have not dealt with my p to the 6th or my q to the 7th. Okay? Well, that's okay. How many times does 5 go into 6? 5 goes into 6 1 time. So this is going to be p to the 1st. And it only goes into 6 1 time with the remainder of 1. So that's why I got p to the 1st on the inside as well. How many times does 5 go into 7? Well, 5 goes into 7 2 times with a, 5 goes into 7 1 time with a remainder of 2. And there's our final answer. Now, there's one other thing to do when you're simplifying radicals, and that would be something that most teachers probably don't even recognize, but occasionally math textbooks do, and that is when you are taking an even root. If you take an even root like we had here on number 4, and you get an odd exponent on the outside, what you are supposed to do is put absolute value bars around that odd exponent. Now, it seems like a simple rule that it actually has gone to the wayside, but what really needs to be represented here is if you're taking an even root, you can't have a negative value here. So because this is y to the first power, that could technically, what happens if y was a negative value? You can't have a negative value come out of the radical if it's an even root. So you're supposed to put absolute value bars every time there's an even root and an odd exponent on the outside. Now, most textbooks are going away from that. So if your teacher asks you to do that, then do it. If otherwise, then you could forget that fact. All right. So part 2 of today's lesson is a lot easier. Part 2 is a lot easier. So much so that I am going to do rewriting in a different video because I do feel like we should just break this up into 2 different things. Okay? Until next time, everybody, stay positive, and I will see y'all later. Bye.